Okay, so let's start with the exercise 1.1. Now we have covered all the topics, so this is the review of these all exercises that the teacher has done. Okay, so I will review exercise 1, 3, 5 and 6. It covers all the topics that the teacher has done. Okay, so let's start with the exercise 1. So the exercise 1, which is on page number 274, the first question states that defects occur along the length of filament at the rate of lambda is equal to 2 per feet. Okay, so per feet the rate is of the events or the defects occurring is 2. Okay, so it wants us to calculate the probability that there are 0 defects or there are no defects in first foot, and the second is to calculate the conditional probability. Okay, conditional probability that there are 0 defects in second foot of filament such that are conditioned on there are 1 defect in first foot. Okay, so now deciphering these questions. So the first one actually says that the probability that in the first foot x of 1 we have 0 events occurring or 0 defects occurring. Okay, so using the Poisson distribution over here, okay, which says that P of k actually it is equal to P of k, it means that the probability that x of t is equal to k. Okay, so it is equal to e raised to power minus lambda raised to power k divided by k factorial. Now here lambda is equal to 2 per feet. K over here is 0 because we need to find out that there are 0 defects. So the k is equal to 0 over here. So putting the values, the probability of x of 1 is equal to 0 is equal to e raised to power minus 2 raised to power 0 divided by 0 factorial. So it gives us 0 e raised to power minus 2. Okay, now the second part, which is a bit tough. Okay, so calculate the conditional probability. The conditional probability that there are 0 defects in second one. So x of 2 is equal to 0 such that are conditioned on that there are 1 defect in the first foot. X of 1 is equal to 1. We need to find this. We need to find the probability that in the second foot we have 0 defects occurring such that in the first foot x1 we have 1 defect. Okay, now according to Poisson, actually according to Poisson distribution, 2 events are independent of each other if they are occurring in different time frame. Okay, now we have 2 events over here, event 1 and event 2. Now when this one event has occurred, the second event actually occurring is independent of this first event. Okay, for example, we are tossing a coin. Okay, here we toss a coin. Okay, so it either gave us head or it gives us tail. And in the second, for example, after 1 minute, we toss the coin again. Okay, so it will give us a head or tail, okay, independent of what it gave us over here. Okay, this result will not depend on this thing. Okay, we cannot say that the coin will give us a head because earlier it has given us a tail. No, there are 50-50 chances that it will give either a head or a tail, and it will not depend on the first results. Okay, so similar is the case with these two events. Okay, so in the first foot, whether we have like a single defect or no defect, okay, this probability that in the second foot we have zero defect, it will not be dependent on this first. So we can say that the probability that x of 2 is equal to 0 such that x of 1 is equal to 1, it is equal to the probability that x of 2 is equal to 0. Okay, because it will not depend on this first one. So this condition is useless over here. Okay, so the probability that x of 2 is equal to 0, it will be equal to e raised to power minus lambda, lambda raised to the power k divided by k factorial. Now here k is equal to 0 and lambda is equal to 2 per feet. Okay, so e raised to power minus 2, 2 raised to power 0 divided by 0 factorial. So it will give us e raised to power minus 2 exactly. So the probability that x of 2 is equal to 0 such that x of 1 is equal to 1, it will be equal to same e raised to power minus 2. So this is the exercise problem 1.1. Okay, so continuing with this review questions. Okay, this is the second problem that we will be doing. This is exercise 1.6. okay, and it says that it is on the same page 274. Okay, let me show you the question also. This is the exercise question 1.6. okay, messages arrive at a telegraph office with the Poisson process with a mean rate of 3 messages per hour. It says that find what is the probability that no messages arrive during the morning hours 8 to noon. Okay, so the rate lambda is equal to 3 per hour. Okay, so every hour we are receiving the messages with the rate of 3 per hour. Now it wants us to calculate the probability, actually the probability that no messages arrive during the morning hours from 8 a.m. to noon. So 8 a.m. to noon is like 8 to 12. Okay, so the total continuity is 4 hours. So t over here is 4 hours. Okay, so we are kind of taking the time frame as 4 hour. Okay, so 8 a.m. to 12 p.m. actually this is equal to 0. We need to find this. So this is the time frame actually. Okay, now here, because earlier actually we used only one foot or one time frame, but here we have like a specific time frame for few hours actually. So what we will do is we will convert this hourly rate into this time frame rate. Okay, so lambda is equal to 3 per hour. Okay, and time frame over here is 4 hours. Okay, so this will be a Poisson with the rate of lambda t. Okay, so over here 3 into 4 is equal to 12. Now for this time frame, actually the rate of this process becomes 12. Okay, so on average we are bound to receive 12 messages in this time frame. So we want to know actually in this first part that x of this 4 is equal to 0. So it will be equal to e raised to power minus lambda. Okay, this will be lambda star. Okay, I will write over lambda star over here. Lambda star raised to the power n divided by n factorial. We can also write k, okay, over here, k divided by k factorial. Whatever you want to write, either n or k, it doesn't matter. Okay, now here n or k is equal to 0 because we want to know that there are no messages. So k or n is equal to 0. Lambda star is equal to 12. Okay, so putting the values. Okay, now e raised to power minus 12 multiply by 12 raised to power 0 divided by 0 factorial. So it will give us e raised to power minus 12. So the probability that in these first 4 hours we have 0 messages received is e raised to power minus 12. Okay, so this is the required result for this part A. Now this question also have like part B. So let us see what the part B says. Okay, the part B actually says that what is the distribution? What is the distribution of time at which the first afternoon the message is received? Okay, so it says what is the distribution of the time at which the first afternoon messages is received or message arrives. Okay, now what will be the distribution? We know that in the Poisson distribution, in the Poisson process, actually the events follow the events time actually follows exponential distribution. Okay, this is known to us. Okay, so the distribution over here is exponential with the rate of 1 over lambda. Okay, 1 over lambda is the mean time that each message is received. So 1 over 3 is the mean time because we have like 3 messages per hour. So 1 over 3 is the rate or the mean time for a message. 1 over 3 hour is the mean time for a message to be received. Okay, and the rate of these messages is lambda is equal to 3. So the distribution is exponential with the rate of lambda. Okay, or exponential with the rate of 3 per hour. It will remain same like given in the question. Okay, I hope you have understood it. Okay, let me know if there is any problem. Okay, so in this review sessions, the next question, this is quite important actually. This is 1.7 and it falls on page number 275 of the book. Okay, this is the page number. Okay, so let me show the question. Actually the question states that suppose customers arrive at a facility according to Poisson process having rate lambda is equal to 2. Okay, now let x of t is the number of customers that has arrived up to the time t. Okay, determine the following probabilities and conditional probability. P of x1 is equal to 0. It means that in the first hour or the first time frame we are receiving 2 customers. The second one is probability that x1 is equal to 2 and x3 is equal to 6. Okay. The third one is the probability that x1 is equal to 2 such that x3 is equal to 6. Condition on x3 is equal to 6. Okay. The D is probability that x3 is equal to 6. Condition on x1 is equal to 2. So we need to find all these 4 probabilities. So let's start. Okay. So in this question, we are given only the rate, that is 2 per time unit. Okay. And we know that x of t is the number of customers up to time t. Okay. So the first thing is to find the probability that in the first hour we have 2 customers. Okay. So using the Poisson distribution, okay, which states that the probability that x of t is equal to n or k is equal to e raised to the power minus lambda, okay, lambda raised to the power k divided by k factorial. Okay, so here we have k is equal to 2 and the time frame is 1. So one of the extension of this is e raised to power minus lambda t raised to power k divided by k factorial. Okay, the t is the time frame. Okay, like in the previous question we had a time frame from 8 a.m. to 12 a.m. Okay, so what we did was we converted the lambda is equal to 3. Okay, we multiplied 3 by 4 is equal to 12. Okay, so similarly if you don't want to do as earlier, we can just do it e raised to power minus lambda t raised to power k divided by k factorial. So here we multiplied this rate with the time frame, so it will give us exactly the same thing. Okay, e raised to power minus 12, just like we did earlier. So if there are multiple hours over here, okay, this thing, then we can use this lambda t formula. Okay, so we can use both. Okay, when there is a specific time frame given, like from 11 a.m. to 1 p.m., then we have 2 hours of time frame, then we use this formula. Okay, if it is given like 2 per unit per time unit, and we are given like in the first hour or in the second hour or in the third hour or in the fifth hour, then we use only the simple formula. Okay, so this is the difference. Okay, so here t is equal to 1 because we are dealing with only 1 hour or 1 time unit. Okay, so putting the values of k is equal to 2 and lambda is equal to 2 and t is equal to 1. Okay, so e raised to power minus lambda into t over here is 1 because we are dealing with only first hour or first time unit, multiplied by 2 raised to power k over here is 2, so it will give us 4. 2 in 2 square is equal to 4, e raised to power minus 2 divided by 2 factorial. Okay, so 2 factorial, actually it is equal to 2 into 1 is equal to 2, so 2 factorial will be cancelled with this, so it will give us 2 e raised to power minus 2. So this is the probability that in the first hour we have only 2 customers arriving. Okay, now going towards the second. Okay, so doing the part B of it, part B says that the probability that number of events in time 1 or unit 1 is 2, and in third hour we have 6 number of events. Okay, now we have and in between. Okay, so when we have and over here, okay, then the probability this is equal to the probability that x1 is equal to 2, okay, multiplied by, now for this thing, okay, the total number of in between hours are 3 minus 1, okay, so what we, x of 3 minus 1 is equal to n minus this one, 6 minus 2. When we have and in between, okay, then we use this formula, okay. What we do is we find the probability for the in between hours, okay. So the total number of events on the third hour is 6, and in the first hour we have 2, so the in between we must have like 4 events occurring. 6 minus 2, 4, okay. So the probability that x1 is equal to 2 and x3 is equal to 6, it is equal to probability that x1 is equal to 2 multiplied by the probability is that in the next 2 hours, okay, x3 minus x1, it is equal to 4, okay. So probability of x1 is equal to 2. This is simple using this formula, okay. Here lambda is equal to 2, so e raised to power minus 2, 2 raised to power 2 divided by 2 factorial, okay. So 4 e raised to power minus 2 divided by 2, which is equal to 2 e raised to power minus 2, okay. So now this is found, but the next thing, the probability that x of 3 minus x of 1 is equal to 4, this needs to be found. Now here we have 2 hours or 2 time units over here, so t over here is 2, lambda is equal to 2, okay, and k is equal to 4. So now we will use the formula of e raised to power minus lambda t raised to the power k divided by k factorial, okay. So e raised to power minus lambda, so minus 2 into t is also 2, okay, multiplied by lambda t, this is 2 into 2, which is 4, okay, raised to power k is equal to also 4 divided by 4 factorial, okay. So it will give us this 4 into 4 raised to power 4, it will give us 256. This is e raised to power minus 4 divided by 4 factorial, so 4 factorial will give us 24, okay. So we can simplify it using like 256 divided by 24 into e raised to power minus 4, okay. This will give us a value of, so it will give us 10.66 into e raised to power minus 4. So the ultimate value is the probability that x of 3 minus x of 1 is equal to 4, it is equal to 0.1954, okay. Now we need to multiply the probability of x1 is equal to 2 with this one to get and. So the probability that x of 1 is equal to 2, and in the third hour we have 6, it is equal to 2 e raised to power minus 2 multiplied by 0.1954. So let's numerate this one also, find a numerical value for this. So this will give us a value of 0.2707, okay, multiplied by 0.1954. So combined it will give us a value of 0.0529 or 5.29% chances that in the first hour we have 2 events occurring and 2 customers arriving, and in the third one we have 6 customers overall arriving. Okay, so B is also done. Now we need to do the C part. Now doing the third part states that find the probability that in the first hour we have 2 such that are conditioned on that in third hour we have total of 6 events happening. Okay, now this is conditional probability. Okay, when there is this sign we have the conditional probability. Okay, so according to the conditional probability equation, the probability that x of t is equal to n such that x of, for example, k is equal to m or anything like that, when you have conditional probability, it is equal to probability that x of t is equal to n multiplied by probability that x of k minus t is equal to m minus n divided by probability that x of k is equal to m. Okay, so this is the equation that we will be using. So according to this, now putting these factors as this one and this one, so the probability that in the first hour we have 2 events occurring such that in the third hour we have a total of 6 events happening is equal to probability that in the first hour we have 2 events occurring multiplied by the probability that in between 2 hours, this hours, which is 3 x of 3 minus 1 is equal to 6 minus 4 divided by probability that x of 3 is equal to 6. Okay, now among these 3, this is simple, this is also simple, and this is something that we need to understand. Okay, so the upper one, the numerator, this part, we already found it over here. Okay, like in this and one, the part B, this one is already found, but I will find it again. Okay, so the probability that x1 is equal to 2, now finding it one by one, okay, is equal to e raised to power minus lambda raised to power k divided by k factorial. Here lambda is equal to 2, k is equal to 2, and t is equal to 1. So we have e raised to power minus 2 raised to the power 2 divided by 2 factorial, okay, which is equal to 2 raised to power e minus 2, and it will give us 0.2707 value. Okay, this is for this part only. Okay, now I need to find this one. So the probability that x of 3 minus 1 is equal to 6 minus 4 is equal to 6 minus 4 is equal to 2, 6 minus 2, sorry, this and that, 6 minus 4 is 6 minus 2 is equal to 4, is equal to probability that in the 2 hours we have 4 events occurring. Okay, so here we have like 2 hours of time, t is equal to 2 over here. Okay, so we will use e raised to power minus lambda t e raised to the power k divided by k factorial. Okay, now t is equal to 2, lambda is also equal to 2, so e raised to power minus 4 raised to the power 4 divided by 4 factorial. Okay, it is equal to 256 e raised to power minus 4 divided by 4 factorial is somewhat 24, I guess. 4 into 3 into 2, 6, 4, 24. Okay, so it will give us a value of 0.1954. Okay, now we have the upper two done. Now we need to find the third one only. Okay, now the probability that x of 3 is equal to 6 is equal to, this is only dealing with the third hour. Okay, one time unit. So e raised to power minus lambda raised to power k divided by k factorial. So e raised to power minus 2 and 2 raised to the power 6 divided by 6 factorial. So let's find a numerical value for this. We get, so 2 raised to power 6, actually it is equal to 64, and 6 factorial is equal to 720. Okay, and e raised to power minus 2, it is equal to 0.1353. Okay, so putting the value 0.1353 multiplied by 64 divided by 720, it gives us 0.01202. Okay, this is the value that we found for this denominator. Okay, now I need to put all these three values into this equation. So probability that x1 is equal to 2 condition on the x3 is equal to 6, it is equal to probability that x1 is equal to 2 multiplied by probability that x of 3 minus x of 1 is equal to 4 divided by probability that x of 3 is equal to 6. Okay, we have value for this, and for this. So putting the values, we get 0.2707 multiplied by 0.1954 divided by 0. Okay, one mistake that I did is that here x3 we have 3 hours, so this is lambda t, and t is equal to 3 hours. Okay, so it will be equal to this. Okay, so it will be e raised to power minus 6. Okay, 6 raised to power 6 divided by 6 factorial. Okay, now simplifying this, it will give us a value of 0.01606. Okay, this is the value, that is 0.1606. This is the value that it gives. Okay, now putting this value is equal to 0.1606, it will give us a value of 0.3292 or 32.92% of chances. Okay, another way to deal with the the conditional is that we have two conditions like given, like in this. Okay, so it can be easily, this is n and this is k, so 6 combination of 2. Okay, this is 1 time and this is 3 time, so 1 by 3 raised to the power 2, okay, and this is 1 over 3. Then the other that remains is 2 by 3, because if we subtract 1 from 1 by 3 we get 2 by 3, okay. So, and here the total is 6, so 6 minus 2 is 4. So using this binomial distribution we can also solve it, and it will give us the exact 0.3292 answer, okay. So this is also another way, a simplified way to use the binomial distribution, okay. N is the second one, K is this one, so N combination of K, okay. For the second term we have the time, first time divided by the second time raised to the power the first, like in we can have like N combination of K, okay. And we have like T1 divided by T2, okay, raised to the power K, and this is the 1 minus T1 divided by T2 raised to the power N minus K, okay. This is the simplified way, okay. I exactly use this one to solve this using the binomial distribution. Now the part D of it, question number 1.7, part D, it says that find the probability that x of 3 is equal to 6 such that in the first one we have we have 2 events occurring in the first hour, okay. So in this case this is actually equivalent to the probability that in the third hour we have 6 hours total, such that in first hour we have 2. It means that in between 2 hours 3 minus 1 we have a total of 4 events occurring. This is equivalent to this, okay. So the probability that x of 3 minus x of 1 is equal to 4, okay, it is equal to e raised to the power minus lambda t raised to the power k divided by k factorial. So k over here is 4, t over here is 2 hours, because we are defining it for 3 minus 1 hours, okay. We have a total of 3 hours, okay, and in between 2 hours we want to find that whether we have a total of 4 events occurring, because in the first we already know that we have 2 events occurred, okay, and in the up to third one we have 6 events occurred, okay. So in between we must have like 4 events, okay. So x of 3 minus 1 is equal to 4. This is the answer, okay. So let's find, so we get t is equal to 2 hours, because duration is 2 hours. Lambda is equal to also 2 per hour, okay. K over here is 4, so finding it e raised to power minus 2 into 2 into 2 whole raised to the power 4 divided by 4 factorial. So we get e raised to power minus 4 raised to power 4 divided by 4 factorial, okay. So we get 4 into 4 is 4 into 4 16 into 4 is 64, and to 4 is 256 into e raised to power minus 4 divided by 4 factorial is 4 into 3 into 2 24. So we will get 8324, and 32 into 8 is 256. So we get 32 by 3 e raised to power minus 4, and the numerical value for this is somewhat 0.1954, okay, or 19.54% chances that we have 4 number of events occurring in between first and third hour, okay. So this is the answer for the fourth part. The only logic you need to understand is that in order to have like 6 events in the up to third hour, and when there are 2 events in the first hour, this is the conditional part, okay? So it means that in between these two we have like 4 events occurring. So just simply finding out for that, we can calculate the conditional probability. Thank you.